So the ZL8800 features a no compensation fixed frequency charge mode control. So let's take a look internal to the device to see how it works. Now the output voltage is sensed differentially and comes back into the device. The first stage we use is a programmable gain amplifier, and this is automatically set up on the device, and we're comparing it against the target output voltage before we go into our ADC. So we're only going to be quantizing the error voltage. This is a high bandwidth, fast transient response, so we're only looking at the relative error in order for regulation. So the next stage is we quantize the error voltage using our high-speed ADC. And from this point on, all the way to the gate drivers, we're going to be in the digital domain. And this gives us a lot of flexibility to use a lot of nonlinear loop compensation. In order to achieve this and ensure the stability of the system, we use something called an ASCR modulator. That stands for a single cycle response. It's a high-speed, high-bandwidth loop control that's used to sit there and adjust the DPWM. So for any load transient that comes on, it will sit there and look at the amount of charge displaced from the output capacitor and put the appropriate signal back on to replace it within a single cycle. The inputs to this block are two. There's a gain setting and a residual. And this sets up the overall transient response speed, and the residual is a dampening factor. It sets the response rate of the loop. From that point of the stage, it's directly to DPWM, so it goes out to the gate drivers. And beyond this, the device will also set up adjustable dead time and optimize the dead time if you're using a dual PWM driver. The best way to take a look at this is on the bench. So I show you some scope waveforms and how the gain and the residual settings affect the overall loop response. To really understand the benefit of the ZL8800 and the no compensation modulator, let's take a look at the performance on the bench. I'm using the dual channel output board for the ZL8800. So this has two independent output voltages, each regulating itself to 1.2 volts on channel 0 and 1.5 right now on channel 1. But for this exercise, I'm just going to use channel 0. So you can see I've got the electronic load connected to this output. For the scope probe output, I'm just going to sit there and have a direct connection right across one of the output capacitors. That way we get a fairly clean pickup. I'm running with a 12 volt input, and I'm just going to use the electronic load box to step between 5 amps and 15 amps. So we're just going to apply a 10 amp load step and look at the transient response. So if I enable this and take a look on the scope on the performance, what we can see here is I've got a 5 amp to the 15 amp load step that's shown in blue, and in purple is the output voltage waveform. With the initial load step of 10 amps going from a 5 amp to a 15 amp level, you can see the output voltage deviation is about 25 to 30 millivolts. That corresponds to about 2% output voltage deviation. That's great for just a standard default setup of the device. So the initial ASCR gain that's programmed through the device is 256, which is a very low setting. That's fine for almost any setup like you use. No matter what output capacitance, inductor, that default setting should come up and provide nice stable, yet fast transient response. If we want to make improvements, we can make some adjustments to it, increasing that gain levels from 256 to 400, 600, 800, maybe up to 1,000 if we really want a high gain output. So let's take a look at what it does and how it affects the transient response. So I'm going to increase it to 400, and as I send the command across PN bus, right away you can see the output voltage deviation drops from about 25 millivolts to under 20 millivolts. So in the scope right now, what you're seeing is this output voltage waveform is AC coupled, and it's about 20 millivolts per division. I can keep increasing it. From 400, now I go up to 600, and it gets even better. Now we're probably about 15 millivolts of deviation for that low transient. We can keep making improvements by continually increasing the gain. So as I go to 800, you can see now we're down to about 10 millivolts deviation. At this point in time, this is probably about the highest gain we'd want to use. Continued gain increases won't really improve the performance of the device. And the reason why is we have the device running as fast as possible. The major limitation now is not the small signal response, it's a large signal response. That inductor current has to slew. So the only way we can get to go faster is to use a smaller inductor value or to use greater output capacitance. So the only downside now of increasing the gain is we're just be adding unnecessary jitter to the system without improving the transient response. So typically this would be what we would consider to be an adequate transient. We're down to less than 10 millivolts deviation on the output voltage, which corresponds to less than 1% of the output voltage, which is a great target to achieve on a power supply. The one other value that we can change with the charge mode control loop is the residual value. Now, as we talked about earlier, that effectively looks like a dampening factor. If we make an equivalent to an analog controller, we can think of it as the phase margin. The lower the value, you're going to see a little bit more overshoot, a little bit more ringing, which just looks like a lower phase margin for a power supply. In most cases, you'll find the value of 90 to be ideal. I wouldn't recommend changing it, but you can tune in the power supply if you want to. So let's take a look at how the values affect the transient response. The default value of 90 is set up right now with an ASCR gain of 400. If I change the residual value down to 60, enter it and send it across the PMBus command, you'll notice two things occurred. The first is you get a little bit more ringing, a little bit more overshoot on the output, which looks like a lower phase margin. The other piece you see is the excursion, the initial drop on the transient response has actually come up. You've actually improved the deviation. And that's because you're getting a slightly faster response to the initial transient event, which corresponds with a lower phase margin system. I can keep lowering it further, but at some point you're going to see diminishing returns. So if I drop it down to 30 and send that command across, effectively there's very little change in the system. So in most cases, the residual has a slight effect. You make a little bit of an improvement if you want to dial in the very last part of performance, but the system will always be stable with the default values of 90, and that's probably the great place to start with. The benefit of the ZL8800 is there's no compensation. There's no complex math. It just works.